Hello everyone, this is Mahdi Nasser Moqaddasi. I'm a distance student and the topic that I'm planning to present today is Hidden Markov Model or HMM. The outline for today's presentation is first we are talking about the introduction and the Markov model, and next we will discuss about the example of the Markov model and start to introducing the hidden Markov model with following of its application. So let's start it by introducing the Markov model with an example. Consider that the weather is divided into the three different types. The snowy day, the sunny day, and a rainy day. Basically, if the weather is considered as a Markovian model, um, the likelihood of predicting the type of the weather for the tomorrow will be only depending on the our observations or our knowledge about the weather today. Basically, what I want to try to explain is if we know that today is sunny, if we have that particular knowledge, then we should be able through the Markovian model to predict what type of the weather will be tomorrow. So to make it a little more theoretic, a Markovian model, the first order of the Markovian model in a Markovian system is only depending on the current state in order to make a prediction of the next step. So you only need to know about the current state to being able to predict what will be the next step. In the next slide, I will talking about the features that are in the Markovian model, what basically it will be included, and we will go through to the each features to know that how we were able to through to the Markovian model to predict the state of the future. Now, back to the previous example, assuming about the for further forecasting with knowing the particular state, the current state, for example, sunny, rainy, and the snow, we want to know that what will be the likelihood of the next state, next day, basically, in our example, to be a sunny day, a rainy day, or a snow day. I will pick the sunny day as our today, assuming the today weather. Uh, what this probability transition matrix will indicate is if today is sunny, tomorrow with the probability of 0.8%, sorry, 0.8 or 80%, tomorrow will be sunny as well, and with the probability of 0.15 or 15%, tomorrow will be a rainy day, as well as with the probability of 0.05 or 5%, tomorrow will be a snow day. So this transition matrix is called as transition probability, which tells us what will be the probability of the particular state with the assumption of knowing the current state that we are in at this time. In the next slide, I will explain that how we are using this Markov transition model in order to making a prediction. So as we discussed in the previous slide, the Markovian model included a set of features that basically with having this feature, we will able to predict what would be the likelihood of a particular state happens. We were discussed that each Markovian model included a set of state, which in our example are sunny, rainy, and a snowy day. And then we discussed that a particular Markovian model would be included what is called as a state transition probability, as is showing in this matrix, It's a probability of going from a particular state, in this example sunny, to the particular state, or basically being in a particular state at then time equals to t plus 1, which is the next day in our example. What we didn't discuss was what is called as the initial state distributions. Uh, what is initial state distribution? It basically tells us that as at the time that t is equal to 0, which is at the beginning of our example, what will be the likelihood that each particular state happens? Back to the example of our weather forecastings, it can be described as in this way, that with the probability of 70% at the time t equals to 0, we will be in the time the weather will be sunny, and with the probability of 25% it will be rainy, and with the probability of 5% it will be a snowy day, which is basically is called as initial state distribution. What will be the initial state? So looking at this pi, we can see that most likely when we are starting to predicting the sequence of forecasting for the next days, the first day will be a sunny day because it has a higher probability. In the next slide, I will explain how the Markovian model works with a particular time series an example, which I hope that it will be clarify most of the aspects that we were discussing in this example. So now let's starting with an example. Assuming that we want to calculating that what will be the probability or what will be the likelihood that this sequence of the weather happens, meaning that what will be the likelihood that this started with the first day of a sunny day, and then after that a rainy day, and then end up with a snowy day as well. So we want to calculate basically this likelihood. In the previous slide, we were discussing that we have one assumption, which is the likelihood that the particular state happens, meaning that assuming this particular state, a rainy day, will only depending on its previous state, which is a sunny day, and this is called as the first order Markovian. So this is our assumption for this particular weather. And then we'll discuss that we have what is called as a transition matrix probability, which gives us that what will be the probability of a particular state, knowing that what will be its previous state. So with this assumption, we will go ahead and start our calculation. So we know that this particular state that we are currently in, this is the first state, is the sunny. What will be the probability of that? And then next step will be knowing that this particular previous state is a sunny day. What will be the probability of that particular day being rainy? And it's going continuing with the same logic of knowing that, okay, if the previous state is a rainy day, what will be the probability that today will also be a rainy day as well? So if you are going with this basically condition of probability and multiply all those values, we will have a likelihood that the particular time sequence, basically what will be the likelihood that particular time sequence happens, which is this value that is showing here. As you see, it doesn't have a very high value, meaning that the chance that this particular sequence happens based on the probability that we have is very less likely. Now back to our HMM or hidden Markov model. So in the reality, or in most of the problem or in the daily basis, we might not be able to observe the actual state, but what we will see is what is called as observable or events. Back to our weather problem or weather Markovian model that we were looking at, we might not know exactly what will be the particular day is, or is it a sunny day or a rainy day. But what we will see is that through to the three basically events or observable, but what people are wearing. For example, if you're seeing a particular coat, you will assume that this is a snowy day. If that's a different dress, like short or a sport dress, it's a sunny day. Or if this is an umbrella in the our observations, that could be a rainy day. So that's what we will see instead of having access to that particular knowledge that what the state is. So here we will have a new term which is called as emission probability. What it says is a conditional probability over the states. We're saying that with knowing that what will be the particular state that we are in, what will be the probability that we are seeing a particular icon, which is nothing but a coat or an umbrella that could be observable. So this conditional probability will be establish our belief on the set of observable that we are seeing. We will using this value in the next slide to see that how now we can predicting forecasting weather just by having access to this set of the observable values. So now, if you want to basically forecasting a particular weather or a time series just by seeing the set of the observations, the formula that is basically indicated here is a conditional probability multiplied by the probability of that particular set of states. So that is what is called that for the all states particular observation can happen. Knowing these values at what is called as a belief, we will be able to predict what will be the output of our forecasting based on seeing this particular observation. What will be the probability of observing a code, and an umbrella, and so on and so forth. Um, this is more close to what the actual real problem will be modeled in the Markovian models and being able to solve. For example, a great example is in the robotic area that the robot is trying to localize itself and finding where is basically it's located as particular time, but it's not able to identify its state. What it can receive is the sensor information that has included with the noise. So once we are modeling in this particular model, Markovian hidden Markovian model, we will be able to see that what will be the most likely position or state that the robot will be located. I will show an example in the next slide of how this model will be look like in a robot localization problem. So the example basically is showing here is the video of the robot that is trying to localize itself based on the information of the sensor data that is received from its surroundings. And while this data is basically gathered using the hidden Markov model and another algorithm, particle filtering, what robot does is trying to consider all the observations and creating a map which is nothing but a set of states of the position around itself. And while these observations, which is a range of the laser beam received through to the robot, the robot will be running its hidden Markov model and trying to see that what will be the most likelihood that it's in the particular positions, or in hidden Markov model, the term is what is the most likelihood that is in the particular states. And based on that, it will like that particular position and showing in the map as it's showing here. This is one of the great examples in robot and robotic, which is called as a robot localization, and the mapping, which robots try to find where it's being located, what it will be its position, as well as finding and creating a mapping about its surrounding based on the data observation that is received. So we will discussing, we already discussed about one of the application of HMM in the robotics, which is also apply into the other areas like medical, finance, speech, and language, as well as everywhere, every single problem that very much you will see a noise and uncertainty in the data that's been received. One of the great areas is speech recognition applications, where the data is gathered through a microphone, has obviously some noise with it, but through the HMM, there should be available a particular word that with some probability associated to it will referring to the word that has been pronounced through the microphones. So this is very much will be a short, brief discussion about the set of the application in HMM. But I hope that it will motivate people who are seeing this presentation, and hope that it's been clear to all that see this presentation. But if you have any questions, or if there's anything that was not clear, please do not hesitate to contact me with my email address, madi.muqaddasi@ttu.edu. Thank you very much.